oui, oui. Oui, 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 oui. Hi, hi, ha, tss, tss, hi, ha.
Okay, welcome all of us. Come here, come back here. The last speaker, Professor David Zhu. David Zhu, professor from University of Alberta. He is a fellow of Canada Academy of Engineering. His research field, urban server hydraulics and smart monitoring, sustainable hydropower and fishway. Students, mixing and water quality modeling of rivers, lakes, and coastal waters. Please, Professor Zhu.
Thanks very much. I will do a shift of the printer, a computer, because I have quite a bit of videos, and that's where I guess the other computer might not be able to play. Let me see, where did that go? Okay. Interesting. Here, okay. All right. So I'd like to thank the organizers for the opportunity to come here to give this talk. This talk is on the eco-hydraulics. My name is David Zhu, and I have a number of PhD students. Rajib, Panchan, Wei Wei is currently here. Matt, Abdul, Wang Ming, and Shantou. So this work is sort of mostly done by the students. Now, so my talk will be mostly on those three aspects. First, about fish entrainment and hydropower intake. At hydropower intakes. So I have a picture here shows laser point. Do you have laser point? Yeah. All right. Thanks. So what we have here is when we build a dam and the fish will maybe suck it into the intake, and that can cause fish risk, can fish damage. So this we call fish entrainment risk. So the question is how many fish will be sucked into and whether or not fish can survive through the intake. So that's this first part. Second part on dam spill-induced gas supersaturation. So what you see is a dam spill water. This water plunging into a downstream river cause the air to be dissolved, supersaturated air. And a group here have done a tremendous amount of work here as well. So the third part is about fishway. So we have a dam, and of course we block natural fish passage. So we need to build a fish to allow fish to move. And I do have another one I want to sort of share with you as a read about air-water flow, and we look at the COVID-19 type of problem. So the first part of fish entrainment. So this is a map of Canada. Now, so what we have here is this is border, 49 degree. This north of this is Canada, US is below 49 degree. So Vancouver is here, it's Pacific Ocean, Vancouver, and Edmonton, that's where University of Alberta is located. So basically what we are looking at is this region. Vancouver has quite moist with the Pacific Ocean. The precipitation, annual precipitation about 1,500 millimeters. And the other side of the mountain is very dry, about 500. So the water rises and goes into this region. That's where Columbia River is really about. So I'll be mostly talking about the Mica Dam, that's most upstream of the Columbia River, and then Revelstoke Dam. Both dams we look at fish entrainment. And then down there we have HLK Dam, that's we look at the gas supersaturation. So in the field work we have, this is the field work we have done in Mica Dam, this most upstream one. So this is a dam and the downstream river, the beginning of the Columbia River. We have students going, Matt Langford and the technician went there, and we take ADCP, this is the dam, the 6 intakes, upstream of the intake. We take a field measurement of the velocity field. So this is, of course, and we also had the field work with fish tagging. So those chips we have, the typical about fingernail size, and those ones were the different type of the tags. And the ones we have is quite expensive, about $500 US a piece, and it's almost like an iPhone, the cost of an iPhone. We have about 300 of those, and we go to about the water basin and tag fish. So tag fish into this, so we can trace where the fish go. So the idea is we can assess how many of fish go to the dam forebay, and after that, then how many of those will be sucked into the dam intakes. So this is numerical model. So we based a field data and combined with numerical modeling. This again is the macadam here, and this upstream we model about 2.5 kilometer of region. This is topography of this. So dam is very deep. It's about 60-meter deep dam. This is another shot of modeling. So this is 6 intake. So the reason we are looking at this one is because initially we only have 4 intakes, and then the dam was constructed in 1980s. That's where Columbia River Agreement, so between U.S. and Canada. So the dam was constructed mainly initially was for U.S. flood protection. So as a result of this, U.S. has to pay Canada $100 million US dollars a year for flood protection benefit. So this was the initial, we have 4 dams, 4 intakes, and then later on, we need to add 2 more, so then we actually have flexibility in hydropower operation. Now the requirement, the environmental regulation tightens quite a bit, and later on when we add into those dams, then the requirement of we have to assess whether or not there is a risk to fish, because you have reservoir in the fish, and then for those reservoirs, of course, there is we start a retention time. So water will be replaced in typically a couple of months, and then the question is whether or not fish will be sucked into the intake. So this is a comparison between the monitoring and the field measurements. So field measurement, different flow condition, and the CFD modeling, and we find that the depth here, so velocity is pretty high, close to the intake. And that's sort of, we have reasonable agreement of the velocity modeling. So that then what we can do is we can assess. So this is, again, we have 6 intakes here. So basically this velocity field induced by operation on 1 intake, in this intake, and you see color contours shows the velocity field. Velocity field due to the operation on 1 intake. And we do have those points. Those points are the fish we actually tracked. So remember I said we put about 300 tags into a fish. The difficulty with that is number of fish you can actually tag or you can monitor more is relatively small. So in this field program, so we were able to tell, we said, well, this is among 300, how many of those tags a fish gets into the forebay. But the actual amount going through the intakes is very small. So in other words, is really, ideally we want to build up the linkage between flow and fish actually being entrained, but the number of fish is too small. So really what we are doing now is we say based on the velocity field, and obviously if velocity is high, then fish within this high velocity region likely will be sucked in by the flowing water. But then, of course, there is also a question about, you say, well, what about if velocity is relatively lower? Will fish, once fish sense the risk, will fish be able to swim away? So that kind of question is still there. For this part, what we did, we said, well, at least we can calculate. If we give a criteria, we said fish, if velocity is more than half a meter a second, then maybe fish may not be able to escape. And then we can say, well, this is a risk volume. So we can do a risk volume assessment. The benefit of doing that is this allows us to change the operation mode. We say, well, if you maybe distribute your flow into different intakes, so hopefully we can reduce the risk volume. So this is the part of what we are doing, and at least we give some guidance in terms of the operation. Now, recognizing the risk, we said, well, we didn't really detect many fish, so we changed another approach. In this one, this second dam downstream of the Columbia River, it's called Revelstoke Dam. Now, again, initially we have 4 intakes, and we are building 2 more intake. That's where fish entrainment needs to be assessed. So in this case, what we did is we said, well, let's do an inventory of the fish. So again, this is a dam forebay, and what we have biosonic monitoring. We have a boat go around and just to see where fish are located. So basically, what we want to see is, for example, is fish live in this area or further away, at what depth. In addition to do a sort of inventory survey, so it really tells us where fish lives in the reservoir. And in addition to that, we can also monitor. We have another monitor here, and this is a fixed sensor. We send a beam down and see whether or not fish cuts through the beam. If fish cuts through the beam, then we said fish is entrained into the intake. So again, to understand how the fish behavior, it does take a lot of work. So this is some quicker result. So what we have fish entrainment number in terms of every cubic meter of water, and this is the distance away from the forebay. So this is really near forebay right here, and we have about 1 kilometer away from the forebay, and we look at fish at a different season. The fish behavior, of course, is seasonal. The fish will grow at different seasons, and also day and night. Day and night is also quite different behavior. So this is just looking at upstream of the dam, how many fish are there. And we also need to know the depth variation. So whether or not fish live on the surface, for example, here, this is relatively shallow, about 10 to 20 meters, or some of those live downstream, a little bit deeper. So again, this will be combined with the sort of risk, again, with the CFD modeling. We understand flow field, a different flow field, and the different combinations. And we know number of fish being actually sort of being sucked into the intake. So this, again, involves combination of the CFD and the number of fish. We can come up with criteria. We said, well, what velocity will actually pose a risk? So this is still ongoing, and processing a number of data sets and try to understand. And this kind of criteria will likely be different for different fish at different season, and even day and night. So in this particular case, we find in nighttime, most of fish, we counted the number of fish. We have about 2 million fish being sucked into the intake over a year, and the majority of those at nighttime. And that's, again, is something which is important. Now, CFD modeling, for the velocity measurement, the CFD modeling, because reservoir is typically stratified, you have temperature stratification, which changes the velocity in the forebay. Now, that velocity itself, the change of temperature stratification, might not be important for fish velocity, because once fish senses risk, fish can swim away, unless velocity is very big. So it might not be as important, but the fact that, of course, the fish may be accumulative surface or bottom is really determined by the relative velocity condition, and of course the food for the fish. So there's a bunch of the sort of complicated things. That's what we need to combine with not only hydraulic engineer, but also with those fish biologists. So second part, we'll be looking at the dam spill induced gas supersaturation. The reason for this is very simple. So if your air bubbles goes into deep of the water, and then bubbles will be dissolved. If bubbles dissolve, then we have supersaturate. So this is beyond saturation, and that can cause fish kill. The team here, Willie Ryan and Li Kefeng, so I've done tons of work on this field. So this is also for Alberta, for BC, Columbia River is also very important. So this is criteria. We want to say, well, what is the risk? How do we assess risk? Assess one thing, for example, which is sort of concentration. We call total dissolved gas. So what is the concentration? 100% is saturation. So this is exceeding 100, so 110 to 115, or 115 to 20, or bigger than 120. So typically, supersaturation bigger than 120 considered high risk. In addition to the dissolved concentration itself, it's also the depth of water. If the water is shallow, then risk is bigger. Now, this is a quick video of sort of, the effect of depth. So this is Coke, and we know if you shake the Coke, of course, your air bubble come out. Now this is, if we take this water bottle to depth of water, this 12 meters, and what you see here is that bubbles doesn't come out. Bubbles all being dissolved in a sense. So this is really effective pressure, the effective pressure of water depth. And of course, this is really changed whether or not air bubble will be dissolved or will become vaporized. So what we have here, so this is kind of real, we are looking at bubbles in water. Now, this is a shot about, of course, we talked about global warming and methane bubbles. So this is lakes in the northern Alberta, Canada, and what we see bubbles coming up. And these bubbles typically are methane. As you can see, if we sort of collect those gas, you can actually see, you can burn it, you can make fire of this. So kind of natural question we have is, if we see bubbles here, and we know the bubbles will rise from the bottom of the lake, and how many of those will actually be dissolved in the water body before it gets to the surface? So this kind of question, of course, we're always curious. It's related to TDG as well, right? So we have air bubble rises, and we want to see how much of air, when it reaches surface, actually being dissolved. So this is a very simple sort of, if you look at air bubble, and of course air bubble has a certain amount of mass in it. And then when it rises, pressure drops, so then air bubble tends to expand. But in addition to this, your air inside of the bubble can be dissolved into the water. So you lose mass while units rises, while pressure drops. In addition to this, this air, for example, if oxygen or then you have water surrounding it, actually has dissolved oxygen as well. So basically, the water, dissolved air can go either way. So this is really sort of, we can study its behavior. So this is when we kind of look at it, we say, well, we did a model of the air bubble simple rising, and you can make quite a bit of assumptions to simplify it. And then we can look at when rises, in this case, what you see, bubble size decrease. The reason for bubble size decreasing while, of course, pressure drops is because the air inside the bubble being dissolved. And the speed of this, of course, controls how quickly bubble size change. So with a number of those, we can also evaluate the effect of depth or initial, including, for example, background dissolved oxygen level. So basically this, again, we are looking at air bubble dynamics. Now, for a jet, if a water jet goes into the air, we eventually will see this jet will break up. And then in this particular case, there is a need. There's some interesting thing we will see a little bit is we say, well, in this water jet, if I add air into this, so what's coming out is actually a mixture of air and water. And this is sort of kind of very simple comparison of the water jet. This water jet, so QA is air, and water jet is 18 liters per minute. We have water jet, and then in second case, we actually put a little bit of air into this. So air is 10 liters a minute compared to 18, and this is 30. So what you see is very, very different behavior. Once you add air into this very quickly the jet breaks up, and then of course becomes pretty much smaller size, kind of rain type of thing. So the reason we are trying this is because we sort of in dam spills. Dam spill, we have water falling into the pool, and but by adding air into this, again, this is no air, just simple water jet, and you see the air bubbles being entrained, and this depth of the bubble can penetrate. But if we add a little bit of air into this, that's what you have, or a bit more air. In this case, air is 20 liters per minute. So this is more than water now. So what we see here is the water, not continuous water jet hits the water, rather it's really water drops, because it really broke up with water drop. With water drop, so the velocity of water drops is much smaller. It's already have quite a bit of air. So by increasing air, add air into the water, what you see here, the kind of bubbles, you get much less bubble. It doesn't penetrate as deep. Plus, if you look at sort of the number of bubbles, you can reduce the bubble size. So one kind of question we kind of think about it, we say, well, when water jet plunging into the pool, if we add air into the water jet, like what we did here, you actually reduce the amount of air being dissolved. So in terms of dam operation, then the kind of question is, can we try to add as much air or aerate the jet before it's plunging into the downstream? Maybe that's one way of we can do engineering approach to reduce the amount of air being entrained. So back to the dam. So this is the Huckinian side. We will talk a little bit more on this as well. So the dam, this one is we call the low level outlet. So water takes from relative deep intake. So typically water from take a deep intake and go through the intake, go to downstream tail race. Usually people believe we do not have source of water. It doesn't really have water sort of being entrained into the water. It doesn't have air entrained into the water. So people typically don't worry about the generation of the totally dissolved gas because they say, well, you don't have water. But the reality is we're in the measurement, in this one, so we have south low-level outlet and north low-level outlet. The difference between those two is the geometry. So what you have is we have the south is a bit shallower, north is a bit deeper. And in this particular case, what we find in the south low-level outlet actually produce TDG up to 130. So it's quite high. 130 can kill fish very quickly. Now, the north, on the other hand, doesn't produce as high TDG. So kind of two questions. One is where air gets into the system, produce TDG. Second is why south produce more TDG compared to the north. So this again is the case. Now, if we look at the detail, we said water air can actually be, we have a gate controlling this, the gate, low-level outlet. Once it's pulled up, and of course we have supercritical flow going down, and then really air can be sucked into this by those gates. So that's what we do. We say, well, then let's do a laboratory study. So this is a laboratory study of very simple. We have pretty much horizontal pipe, supercritical flow coming down, and you have hydraulic jump, you have tail race, and the water is much deeper. So depending on the tail race water level, if tail water level is very low, like what we have supercritical flow going through the pipe. And if it rises, you have hydraulic jump. And if it rises further, then hydraulic jump may be forming but not going, sort of extends through the whole pipe. So really a different region. And if water level is even higher, okay, it's even higher, then this hydraulic jump may even be submerged. Then obviously these all affects how much air can be actually being sort of being entrained into. So really we are looking at, we said we have a pipe, supercritical flow, and we're interested in how much air can be sucked into this, and of course it's brought out by hydraulic jump. Even without hydraulic jump, for example, in this case, we have supercritical flow going through, and you can actually find, this supercritical flow, water is flowing much faster, so then obviously it can suck in quite a bit of air as well. So basically we are interested in what is air demand in case like we have supercritical flow. So this is sort of experiment we have hydraulic jump at the end of the pipe, and then with tail water level rises, hydraulic jump being pushed further upstream. And of course when water level is really high, the supercritical flow is sort of the gate being submerged, and then you do not have much of air demand. So this is what we have. We can calculate relative air demand. We call it beta. Beta is percentage of air, or just air flow rate versus water flow rate. So what we see here different regimes. I'm not going to do too much of detail of those regimes, but we have different regimes. Regime 2, for example, we see data point about, we say 10%. So the air flow is about 10% of water flow. Okay, water flow rates. And then, of course, depending on different regime, tailwater is really high. We see those data points. It actually gets very small. So this is 5% of the air compared to water flow. And this is only about 1 or 2%. Now, in most cases, we don't even worry. We say, well, if airflow is so small, if down to this kind of regime, it's so small, we don't even worry about this. In most of engineering work, we don't. But in the air TDG problem, it is actually very important. We will show a little bit later. So even with airflow of 0.5%, not even 1%, 0.5% of the airflow, once it's dissolved, can produce TDG of 130, which is again toxic to fish. So once we have sort of understanding of how much air can be sucked into this, and then we say, well, next question, we say, why south low-level outlet compared to north produce so much less or so much why south produce more TDG. And this is kind of counterintuitive because south is much shallower. So as we were just talking a little bit earlier, we said, well, water, if it's deep, then water tends to be dissolved more. But in this particular case, south actually is shallower than the north, and we believe the reason for that is because the flow is supercritical flow, and this shallow is much more turbulent. Turbulent kinetic energy is much bigger, as you see the colored contours. And with higher turbulent kinetic energy, you produce much smaller size bubbles. If bubble is smaller size, again, it enhances mass transfer. So again, this is the sort of what we believe, and what we did here is we did some comparison with the sort of this air, again, air volume. So the relative airflow, is what you see here is again 0.5% of the airflow of the water, north and south. In terms of airflow measurement, we did airflow measurement, and it's not that much different. Now, what we find is very different is here, because of air bubble size of air bubbles, the south level outlet is actually, what you see is sitting on the higher end. These are red dots. South is much higher than the north because of much smaller bubble size, much stronger turbulence. So with those, then we come back to look at the Columbia River again. So this is the third dam, as I mentioned, in the Columbia River system, and this goes to this is through the dam, and I have another shot where this comes into this. We have a number of dams coming in. This is Brilliant Dam, and down below is another dam, 1 liter dam. So we have a system where we have multiple dams. Now, in this particular case where, again, because this is a cross-border, cross-boundary river with US and Canada, and in US always tell Canada, say, well, when water comes into the border, it's already 130 TDG, which is already toxic to fish. But then what is the reason for high TDG water to the US? Actually, what we find is due to the US. So there's another river here. This is the river system. So that's actually the river and then the US dams. US has a boundary dam. This goes up and then feeds into the water, come to the river. So basically there's multiple dams, and the impact of multiple dams on the actual TDG, which we see the water goes back to the US. So this is the case then we actually do the field monitoring. We say, well, let's do, so this is the platform we have for measuring the TDG. So we want to see what is dissolved gas in the river. And then we also did ADCP and to obtain flow field. So we have a number of stations. We have a number of stations, and also all the way upstream as well. We look at the contribution of, for example, the dam spills versus generation, et cetera. So that's sort of quite a bit detailed work. I don't want to get into too much of those. And the generation of TDG also changes with water. As you see here, this is 7 Mile Dam, the one of the dams in the system. And you see water is quite a bit of white. So what you see the white water is because it's actually turbulence penetrate to the surface, and you see a lot of air actually gets into the water already. And then this water, and of course, pretty much like a Coke we have seen. If we shake the Coke, make turbulence out of this air, it tends to leak out. So if it's supersaturated already upstream, and when it goes through this, then obviously air can be released back into the atmosphere. And then, of course, you have ski jump and plunging to pool. So these different processes can either reduce the TDG or add or can reduce water, dissolved gas, or add dissolved gas. And of course, in the river itself, there is also the mixing, transverse mixing into this, because if water comes into part of the river, it will eventually mix across the river. So this is, again, and itself will be, like in the morning we hear talk about surface aeration. Air can be added into water by surface aeration, but then this can also dissipate as well. It's pretty much similar process. So that's where we have various systems we put together into sort of a sort of risk map. And from hydropower operation-wise, really what they need is tell me how do I operate so this is the HOK, this is Juanita Dam, this 7 Mile and Boundary Dam upstream in the US. And you kind of look at it, you say, well, how do I change the operation of the system to reduce the overall TDG, so which is shown in the color. So this is just TDG map, but then of course, in terms of risk also is involved with sort of threshold. What is the value of TDG? As I said, 110 is kind of okay, 100 more higher than 120 is a risk, and also water depth, because depth has pretty big effect as well, and then you also have exposure duration. So this again allows hydropower company to evaluate the risk, and then they can do adjustment of how they operate the dam. So now the third part I want to move to is about fishway study, and we have this is the vertical slot fishway, and I'll also talk a little bit about nature-like fishway. So this is another river. This actually is the Fraser River. It's a salmon fish. This is a picture we took when we went to field work in late August. Late August, salmon fish come to the dam. So this along the river, and this is fishway here. So the water is releasing and really guide the tail fish that come here. This is, this is the way you move up. So fish supposed to come here and find the fishway entrance, take a turn at the stacked fishway and go upstream. The kind of question here is, again, this shows a fishway called a vertical slot. It's a slot here, and so fish pass through this, can stay here for a while. And again, this is another map showing sort of the plan view. So this one called a fish water release gate. So really allow water to release to guide the fish, to allow the fish to move upstream of the river. And this is again vertical slot fishway. So I just want to mention about this fishway. So how do we guide the fish to find the fishway entrance is really the important. Now what this one we are doing here is we have fish, and those are 1, 2, 3, 4, 5 is the position of the fish. So this is fish is being tagged, and the fish tell you and how long it stayed in position 1, 2, 3, 4, 5. And this allows to assess whether or not the fish has difficulty find the entrance and move upstream. I just want to quickly say that again, this is sort of different gates we can control to this release water to allow fish to move up. I just want to mention about hydraulics components. So depending on how water is being released, and we have water release, you create a different circulation eddies, and these circulation eddies can be confusing for fish because fish really go upstream. And now you have a big eddy, and when fish comes in here, fish really doesn't know where to go. Do I go up, go down, or go up? So that's where this particular study is really about how do we release water to produce the velocity field that allow fish to quickly move upstream. Because from those fish tagging, we find a number of fish actually very exhausted by the time it's moved upstream. And that's where, or got delayed in terms of getting to spawning field. So this another fishway is in Montreal area. So again, this is 49 degrees. As I said, US is lower than 49. This Canada, this St. Lawrence River, and we are looking at here a fishway next to Montreal. Okay? So this is the park we are dealing with. So this is the fishway we have, and the fish go upstream, downstream, take a few stacks, and this is a construction shot. Somebody standing there shows you the scale of the fishway. The fishway is used for sturgeon fish and American eel and copper red horse. So those ones are considered endangered species for the North America. And sturgeon, of course, we have Chinese sturgeon, right? So this is actually one of the longest and the largest and longest living species. And this sturgeon can live over 100 years, which is very long, I guess, compared to, I guess, human life, right? So it's about comparable to how long we can live. Typically, it takes about 20 years before it matures to be able to spawn. So really, we want to make sure it'll be able to spawn, go upstream, sort of in this time frame. So we had this technician we have, and we sent a technician over to take the measurements in the in this. And really in this one, remember they said it's stacked. You go upstream and you turn around. So we have turning pool. So the question about turning pool is, in this case, we find the turning pool is really becomes a difficulty, a barrier for fish. Fish comes up and tends to sit in the turning pool, decide not to go upstream and then go down. So this fish is, of course, very different. And for the salmon fish, earlier we talked about salmon fish will try to go anywhere. It can go upstream. Now, the fish we just talked about in these fish, it doesn't really have to go upstream. So when it gets frustrated, it doesn't really know with this kind of circulation eddies, doesn't really know and just tend to give up and actually move down. So really, this is one what we are looking at. We said, how do we design? How do we design sort of particular, for example, geometry, the length and width ratio, and then of course also the turning pool, and that's where sort of we give different design criteria for people to use. And this is in the lab. Similarly, we did a laboratory test, and we can measure flow field and circulation eddies for different geometry and flow condition. So this is what we want to move on is. The trend is we say, well, can we avoid those concrete structures? We call it natural like. So this is in terms of natural like, and of course you see the naturals, you see rocks, right? So this is a small dam, and then you put the rocks, and then you rock where fish can move up and down. So it's what's called a rock ramp. And then you have pool and weir. So these different type of sort of pretty nature-like system. So we did some hydraulic model test of those. We put in the rocks, as you see those rocks here in a flume, and we have different arrangement of rocks to see what kind of velocity field and what kind of, including, for example, energy dissipation as well. So this is some picture showing we have color dye and the kind of flow field, and we also have numerical modelings of this, try to understand the flow field. This is just quickly go over. So this is one called a weir. So we can put rocks, so-called weir, pool and weir. So we have pools, this weir, and the weir can be different arrangements. This V can be towards upstream or V can towards downstream. And what is spacing of those for different design? Again, this is we can do the laboratory testing, and we also can do numerical modeling. So we can do all sorts of the measurements, and for different geometry. So with this one, actually, we apply this in the northern Canada. So again, if we come to map, so this is northern Canada, US, again, 49 degrees. So Vancouver is here, Edmonton. So we come up to here, the diamond mine. I guess if those of you sort of need to go look for diamond ring, and you pay attention to polar bear. And this is a brand name called Polar Bear. It's actually a pretty good one. So those diamond mines, and what you see here is a lake. So diamond mine is formed when volcanic lake is formed. So basically your volcanoes formed, and then you have volcanic lakes. So basically these mines are at a lake site. So if we want to do mining, and if we see this is mining we have now, so what we have, this is a truck carries 400 tons and go all the way there to dig out the mine. So if you look at mine, really what we have to first to drain the lake. So basically the lake has to be drained. You have to get rid of all the water. So do the mining, surface mining, and then obviously you impact the habitat. So one of the requirements is you have to compensate for the lost habitat. So one of compensation here is then we say, well, how do we create various units of habitat? So then we allow sort of compensate for the lost fish. So this is a study we look at. So the upstream lake is headwater lake. So basically there's no fish there. But then downstream has a bigger lake. So what we are looking at here is we say we can connect these two lakes with a stream, a fishway, basically nature fishway. So if we can create this, then fish can move up and down, and you add units, fish habitat units in the upstream lake. So basically, this is what we want to do is we create sort of a nature fishway, and this is a very northern part of Canada where nobody wants to see concrete. Okay, it has to be rocks or trees, those kind of things. And there's a challenge with this. Part of the stream is actually 15 degrees steep. So it's very steep. So that's where what we do is that we do this with rocks. We arrange those, and then of course we actually put a fish into the downstream and see how fish actually move up. So the advantage of the northern Canada, because it is the summertime, so we can put a camera there. Summertime, as you probably know, the daylight is almost 24 hours. So there is a cafe called the Midnight Cafe. So you can go there 12 o'clock at midnight, still bright, still daylight. So for us, it's actually easy. We put a camera, we can continuous 24 hours, we can monitor, we can see how fish uses a place during the day, during the night, which pool it uses. So these are sort of fish, and we can tag them, and we can sort of build this up. And occasionally you lose fish. We lose a number of fish, and we look at video image, and you can see this polar bear. So polar bear, it becomes polar bear's dinner, I guess. We lost a few of those. So basically with this, we can come back to design. We say, what kind of pools, what kind of velocity, depth, or daytime, nighttime, which actually works particularly good for fish, and that's why we can look at called fish usage. So we can do those. Okay, so I want to do, before I close, I just want to a little bit of the other stuff on air-water flow. Now this is COVID-19, okay. COVID-19, of course, is, we do quite well in China, but in US or Canada or Europe, it's extra, it's very, very severe. So we actually got 3 research grants related to COVID-19, and the ones we are working on is really look at air-water flow. So you have somebody sort of, coming out talking, and you have droplets being produced of various sizes. Now, the kind of question you probably know, we have sort of requirement of you keep distance of 2 meters apart. The reason it's 2 meters apart is because for big drops of 100 micron tends to fall before, before it hits other people. If we stay 2 meters apart, you're okay. But that's not true for very small ones. So the small ones I've shown here is typically if we talk about 5 microns, okay, so 0.05 millimeters. If we talk this size, and you can actually have a number of the viruses stay with this, and with 5 microns, they can stay suspended in the air for a long time. So we are looking at, the reason we are looking at this is because wastewater actually, we found a wastewater sort of virus in the wastewater. And the kind of question is wastewater, when it transports, when it hits, then whether or not these viruses in the wastewater can be resuspended. Once it's resuspended in the air, can be moved in the air for a long time. So this is really what we do. And we did some shadow graph on this. That's typical, probably. You probably see, you have a water drop falling down, and then you produce kind of crown, and you have very sort of secondary drops being produced, and we can do those. Now, because the aerosols are so small, we can actually make use of another technique called Mear scattering. So we shoot a laser light, and then it hits the drop, which is typically circular, because once it's down to 5 microns, it's pretty much circular, and you have light being scattered. The scattered light can be connected, and then you see the impingement patterns. Basically, you can see those patterns. By examining those patterns, we can detect, we say, how big are those size of those tiny little drops. So basically, that's what we are looking at. So the first phase of this, of course, we have water jet, and what you see water jet initially continuous, then break up into a different breakup model, which is classic fluid mechanics. And what we have here, if we look at jet, it may not break up, so basically it has to pool, and kind of you have kind of shock wave or then spread, and you may produce this crown, pretty strong crown, and you have secondary droplets, or you have some in between. So really it's not quite broke, and really you have kind of big knobs. And these, of course, we can measure those. We did some size distribution and velocity distribution. Just typical size distribution dominated here is about 1/10 of the drop size. So I guess it's sort of majority of those drops are typically about 1/10 of size. So this is about 0.1. And if you look at velocity, it's typically bigger than your initial velocity. Some of the velocity can go actually to about 2 times. If your drop hits this plane and actually produce a drop of 2 times faster. Okay, I just quickly again show some of those ones. So this sort of, again, you see the different behavior of the drops being produced. And the last one actually is if a drop hits a powder. So this has some implication when we look at sort of urban, for example, with rain hits the soil, etc. So basically you see all sorts of different behavior, and this research is still ongoing, and we are looking at the, is viruses, aerosol containing viruses, and it kind of shows is this is spherical aerosol, and if your viruses contain, your infringement pattern changes. And by examining the pattern change, you can actually learn quite a bit more of what's in there. Okay, I know I'm 1 minute over. So then, of course, just quick comments, I would say remarks. The basic air water flow is everywhere. It's important, and we don't know a lot about this. And then, in particular case, in our hydrolysis, we need a field lab and a numerical modeling, and it also involves environmental and biologists as well. Currently, of course, another thing we are looking at right now is we said we want to study climate effect, how the climate effect is changing, impacting on the reservoir operations. Okay. Thank you very much.
Thank you, Professor Zhu. This is an interesting report. Ask a question, please.
People want to finish, I guess. Well, I will be staying around, and we can chat. So.
Thank you, Professor Zhu. Here. So, here.
Okay,
Thank you, Professor Zhu. I have a question about the rock-made or boulder-made fish pathways. So did you compare the efficiency of the rock-made fish paths with the traditional concrete ones? Which one is better, or we have to sacrifice some efficiency for better ecology?
Right. I guess the trend is people want to move to the kind of nature-based rocks, for example. There are concerns. I guess we had to talk yesterday about Netherlands, of all nature-based solutions. The question is whether or not these can sustain or withstand extreme events. We had cases where fish were built a kind of nature fish habitat, when a big flood comes and all wiped out. So I would say the engineering concrete is easier design, but I would say nature-like is a trend. It is a trend, but the question here is, of course, quite a bit of engineering work. How do we make sure how it performs? This performs easier to study for whatever design condition, but then, of course, how do you make sure it can withstand different flow conditions? If we put a rock in the river and sediment erosion will tell you very quickly, it's going to change very quickly. So there are different issues, I guess, we need to study, yeah. Okay.
Okay, thank you.
Okay, thanks.
Thank you, Professor Zhu, for the very interesting topics. I've got a question, not that technical, but probably more in terms of some policy, because you mentioned that the Columbia Dam is sitting on the boundary between Canada and United States, and maybe there are some similar institutes here in China, but maybe, for example, if we build a new dam which belongs to the Ministry of Water Resources, but long in the downstream area, when the discharged water affects the fish farming industry, which belongs to maybe the local government, and of course the two government departments cares about different things, and if, for example, the loss of fish is caused by the flood discharge, sometimes some agreement or has to be reached between in terms of the policy making. So my question is that, to your knowledge, for example, in Canada or American, are people aware of this kind of additional cost that may cost due to this kind of thing when building a new dam, or do they have any strategy to solve this kind of things? Thanks.
Okay, yeah. That's a very good question. And the transboundary water management, I guess, Professor Chen probably can tell quite a bit about those. Columbia River management, because it's between Canada and the US, this is one of the classic textbook cases in terms of very good collaboration between two countries. And I know with the Mekong River and the downstream dams, there's quite a bit of debate, dispute. In terms of for the local, I guess Professor Lee was sort of have a project right now on with dam spill destroyed, cause fish kill. I guess there's some legal frame, legal aspect, and I guess that's sort of more policy, as you said, policy and the government issues. That's beyond hydraulic engineer. We provide advice, basically. We tell them, we say what we think is a reason. And then they have to adapt. Okay. Yeah.
Professor Zhu, very interesting talk. My question is that for this very expensive biosonic sensor, what is the weight as compared to the weight of the fish itself? I'm wondering whether this will, when you inject in the fish, whether it will affect the fish swimming ability, and so the result will be different compared with the real one.
Yeah. Okay. Yeah. Thanks very much. So this is a good question. So typically, this is about nail size, about half a centimeter size. We put it in the back of fish. So there's a requirement on the fish weight. Usually, we have to limit to the 1% of fish weight. Cannot be very heavy. So the fish has to be decent size. And then there's various different sort of procedures in terms of making sure fish can recover. This is biologist sort of does this. I'm not me doing this. We actually have, because it's very expensive, so we actually around, because some of the fish may be captured by farmers and fishermen. We assign telling them if you find it, return to us, because $500 a piece. Very expensive.
So what's the percentage you recovered for this?
10%.
10%. Okay.
Just most of this guy got lost. Again, this is by government requires hydropower to do this, right? So we spend tons of money buying those chips. Yeah.
Okay, Professor Zhu, very interesting talk. I think Professor Chen asked me to convey a question. Actually, the first thing is I would like to know the depth of the dam, or the height of the dam, or depth of the water. This, because for the high dam, more than 100 or 200, you have the fish swimming up, or you lift up to the reservoir, but they already lost the habitat. So actually, there's no. It's not meaningful to do this way. That's one question. I would like to ask for your comments. The second one is about the TDG. The dissolution of the air in the water is different from the bubble, I think. So my question is, the dissolution is from the dropping period or in the energy dissipation pole? The second question.
Okay. The first question about dams. Now, in Canada, the dams I've talked about, we do not have fishway. So basically, it's very upstream of Columbia River. U.S. already did all the damage. So when the fish comes in, so the Columbia River goes down to the U.S., turn around to Pacific Ocean, and there's quite a few big dams in the U.S. And that's where they worry about fishway. Salmon fish basically cannot get there. So. But we do have fishway, and I actually have some slide on other dam, which probably can show this. So this, some of those, this is for fish tracking. So we need to get into the fishway, and then you see the truck and the top end. So basically we do various kinds of things. And the fishway typically used for small dams. So the dams I talked about with Mike and Ravustuk more than 100 meters high. So basically, there's no way, and very downstream. And those ones, this is a new dam we are looking at. It's run of the river. I think the river you have a small dam. That's where sort of you have the fish will. This is a temporary one. The first fish oil was developed in Canada. That was 1940s. One very early on. But I guess China is doing a lot more work on fish oils compared to because of hydropower. Now, second about air bubbles. Air bubbles air goes both ways. So really depending on the partial pressure of the, of particular gas in either in water or in air bubble. It can go both ways. So when air rises, not necessarily, so you lose air. You can lose air, but you can also gain air if you do not have enough. So it's really controlled by the partial pressure.
No, my question is the air entered the water during the dropping is different from the air that was dissolved in the water.
Right, yeah.
For example, the sugar, we put the sugar in the water and then we stir it and then it's dissolved. So it's kind of solution, But the air bubble, which is different from the dissolved air.
Right, yeah, true.
Yeah.
Air
So the damage is made by the air dissolved in the water.
It dissolved, yes. Yeah.
We must clarify that. Then the question, the following up question is in the downstream. I'm very much puzzled. You have the water depth about 1 meter and 10 days exposure, and then you have a risk.
Right.
So I'm not sure the river you studied, but 1 meter depth is very, very shallow.
Yeah, so that compensates, every meter of depth compensates for 10% of TDG. Now, the kind of question is sometimes fish may not want to go deep. That's again with fish habitat. Some of fish actually stay shallow without recognizing the risk of shallow water. So I agree with you. So what you said is right. So basically, forming bubbles is because the gas is supersaturated. So it dissolves the gas. That does all the damage. If it's a bubble, it's just right.
Yes. So if you have a water depth larger than 10 meters, something like that, then the damage is much, much less.
That's right. So basically, you don't have, for TDG, it compensates for those. Usually, you don't have the risk, but you have to go deep. So that's whether or not fish knows it. Professor Lee did some experiment, right? How the depth compensate for the TDG.
Okay. Do you ask a question?
We can chat after as well. I know, we have award ceremony. We have students anxiously waiting to get this award.
Dear Professor Zhu, I'm from Sichuan University and I've researched the effect on fish of TDG for a few years, but sometimes I want to give up because in fact my research is not cannot be used to the real
engineering
project.
problem.
So I wanted to ask a question. So, do you have any efficient way to solve the problem?
I guess this is a common sort of dilemma when we do PhD. We say, well, it took a long time. We don't see where the end is. Now, remember the beginning at this opening ceremony, Hubert Johnson, he talked about, he said, well, with even very, very simple step spillway, he said, we still need experiments. We need physical models because its air-water interaction is quite interesting. It's actually very difficult. So it's a lot of very interesting stuff in it, I guess. So you probably will find it interesting. Once you get into this.
Okay, because in some times which was built here, we kind of change the time.
True.
So I'm confused how we can do.
Right. Yeah. I guess dam is difficult because you have dealing with huge amount of flow, whether or not you can engineering solutions but that's where research is about. That doesn't mean we have solutions for every problem. So, but we try to understand those. I guess that's probably the first step, right?
Okay, thank you.
Okay, thanks. I guess we are done.
Okay. Thank you, Professor David Zhu. Thank you very much.
Yeah.
Thank you again. Okay, everyone. The last games. Guests of and friends. The conference is come to the end. Since the issue of the first round of announcement on February 5th, we have heard from more than 400 scholars, college and friends from 55 institutes in 11 countries. The conference received the total of submission of 227 abstracts, 36 for paper and 25 posters. During the 3 days events, 133 scholars given 5 plenary speeches, 20 keynote lecture and 7 academic presentation of the theme of water crisis and disaster mitigation, water pollution prevention and control, water ecological conservation and restoration, and frontier in water science and technology, engineering. A total of 281 registered delegates participated in this conference, including 33 online participants and 248 on-site participants. The live broadcast of the opening ceremony and planning speeches on July 7th was watched from 16.5 thousand times, and the photo gathering was broadcast for over 82,000 times. A 403-page conference proceedings entitled Advance in Water Disaster Mitigation and Water Environment Regulation is published by Sichuan University Press after reviews of the technical content. Yesterday, 40 delegates joined the technical tower to the Chengdu Planning Exhibition Hall and the Guixi Park for an on-site investigation of the water government and urban green development in Chengdu. An important purpose of organizing this conference is to provide a platform for our young researchers to present their work and to communicate with colleagues and friends. Therefore, we prepare here several conference awards to be guaranteed to author or present under 35 years old. First, 4 best poster awards are selected from the total of 28 poster presentation. The presenters are Liu Jieqing from Hehai University. Please. Tang Rongcai from Sichuan University. Sun Juying from Institute of Mountain Hazard and Environment, CAS. Please. Sun Juying. And last, Hu Yong from Wuhan University. Please come to the forum and please let us welcome Professor Chen Qiuwen from Nanjing Hydraulic Research Institute and Professor Nie Ruihua from Sichuan University to present to the press to the winners. Please come here. 那个证书呢？ Congratulate them. The second award is the Grant Award and first prize for oral presentation. Among the present under 35 years old, the winners of the first prize for the honor presentation are Pan Jiajia from China Institute of World Resource and Hydropower Research. And please here, come here. And Li Manjie from Tsinghua University. Zhao Weiyang from Sichuan University. Yang Zhuoyuan from Wuhan University. Wang Jian from Shanghai Jiaotong University. Chen Sixue from Zhejiang University. Please, the winners come to the front and please let us welcome Professor Yu Xiping from Tsinghua University and Professor Li Kefeng from Sichuan University to present the prizes to the winners. Congratulations. Okay. The winners of the grand round for oral presentation are Xiong Yan from Hehai University. Chen Zhixin from Dalian Maritime University. Maritime. Please come to the front. And please let us welcome Professor He Qing from South China Normal University to present the prize to the winner. Thank you. The last award is the Best Paper Award. 2 papers are selected from the 4 papers that we receive on the 4 themes of the conference. Based on technical review, the first author is Wang Hualin from Wuhan University. The total of paper is China Evolution along the Yang Yichang Chen Lingji Ridge downstream of the 3-gauge dam. The next, Li Wuhua from South Chinese University of Technology. The title of the paper is Comparisons between SWOT and SWOT plus for simulation agriculture management in the large watershed, a case study in the Jiang River Basin, China. The next, Zhou Qihang from Sichuan University. The title of the paper is Experimental Study on Response of Bed Morphology and Water Level to Unsteady Sedimental Supply. The last one, Song Xiaolong from Tianjin University. The title of the paper is Experiments on the Deterministic and Non-Deterministic Effects of Water Inflow on Channelized Configuration during the Lagos-Trine Delta evolution. Please. Next, please let us welcome Professor Chen Xiaotao from China Institute of the Water Resource and Hydropower Research, and Professor Lin Pengzhi from Sichuan University to present the prize to the winners. So, okay, please join us to congratulate all the young winner again. Please allow me to present the conference organizing committee and the state key Laboratory of Hydraulic and Mountain River Engineering of Sichuan University to express my gratitude to all distinguished guests for the support to the conference. I would like to express my thanks to the co-organizer, Journal of Hydrodynamics, and the sponsor RAHR and IHR China chapter. Thanks to all participants and our 24 volunteers who have granted the smooth operation of this conference. In the end, I hope you have a pleasant experience here and have a safe return trip. I'm looking forward to our next reunion at the third WDWE. This conference in 2 years. See you. Thank you everyone.